So today is our lecture 12, and we are going to start studying convolutional neural networks. So what we have covered so far is logistic regression, and then we extended the concept to multi-layer perceptron, and then we converted those shallow networks to deep networks. We studied various techniques to optimize deep neural networks. We have the understanding that MLP is a fully connected network where all nodes are connected to the nodes preceding and following them. So if we have an input vector, we have the weights on each weight matrices on each between each layer, and we have a weight value on each of these lengths, and all of the nodes in one layer are connected to all the nodes in the next layer. So this is your input layer, then you have your hidden layer 1, then you have your hidden layer 2, and then you have your output layer. So a fully connected network where the links, all the nodes are connected via links. And in today's lecture, we are going to cover convolutional neural networks where the nodes have a partial connectivity to the nodes preceding the current layer and the previous layer. So all the nodes are not connected. We can have sparse connectivity between one layer and the next. So these convolutional neural networks, they are composed of the input layer, then we have the convolutional layer, one or more, we have the pooling layer, and we could have subsampling layers, and then we would have the output layer. where we can have our classification, our regression outputs, so this is the structure of our convolutional neural networks. And before the output layer, we would have the fully connected layers, one or more, and then we can also have the global average pooling layer. Instead of your fully connected layer, you could also have average pooling layer before your final output layer. So this is the general structure of our convolutional neural networks. They are also a type of neural networks, and they are characterized by the property that they can learn directly from your data. And usually they are used, wait please, they're able to learn deep learning, where the model learns directly from the data, and they're useful for finding patterns in images, to recognize objects, classes, and or categories, and they can also be used to classify audio, time series, and or signaling data. So these are some of the application areas where we can use our convolutional neural networks. And why they are used? So they have the property that they can reduce the model complexity, because not all the nodes are connected to the next layer via links. We have a partial connectivity. This reduces the model complexity. Why? Because we are reducing the learnable parameters, the weights in the links. There, for example, the weights are significantly reduced, and we have partial connectivity, and the weights are shared, categorized by convolutional neural networks, and mostly they are specialized to sequential data such as images, speech, and text. So here we have shown a neural network architecture where we have a connection from the first layer to the second layer, hidden layer, and then we have the output layer. So all the nodes, for example, if we take this node and we have 3 nodes in the next layer, so there would be 3 connections coming out from this node. So now if we check the nodes connectivity for this node, it should have 3 links connecting to the next node. So we have these fully connected networks, and in case of convolutional neural networks, Let's check the connection for this node. So it has only one link coming out of this node, and for this node we have two links. In case of the third neuron in the first layer, we have three connections. So the connections between the first layer and the first hidden layer, they are sparse. They are partially connected. Since the number of weights we have here is significantly larger, compared to number of weights in this network, therefore our model becomes less complex to train while achieving nearly the same performance or even better in some tasks. So what is an image? Let's see example of image classification. An image is basically 2D representation of your pixels. 2D image, and let's suppose it is two-dimensional array of pixels. So each pixel will contain a value, and then it will go through the classifier to predict either it is X or it is O. So that is the target of image classification example in this example. What about if that image is translated? It is shifted. So this is the original image, then it is shifted to the left, then it is reduced in size, and then we have distorted version, different version of our X, and our classifier has to identify all of them as X. Then we have an example that our image is rotated. It may be rotated, or it could be scaled, right? So we have different versions, and in both the cases our classifier has to determine the classification either X or 0. So how can we determine that both of them are basically X? How can we do that? For the machine learning CNN network, how can we determine that they are both the same? So this is a distorted image of the original image, and we have to determine that both of them are equal. So what we can do in our machine learning algorithm CNN, we can find a partial matching. So we can say they are both partially matching, and what we do is we try to find the local features within the image. So this is a local feature, both of them are matching. The central part, at least, it is matching. This part is matching. So we try to find these local features within the image and then determine if they are both the same images. So how can we find these local features? Local features means the features or patterns within your image. In this example, the specific image that is under consideration, find the local features and then match them. So how can we do that? Using convolutional, and this is convolution can be one way of finding local features within or extracting the local features within our image. Let's suppose this is our image and this is the mask that we have, and we multiply them. This is I and this